Welcome to Lesson 3, Continuity. Our objective in this lesson is to use the formal definition of continuity to determine if a function is continuous. Now, I know in the past you may have been able to say that a function is continuous if it has no breaks or no holes, and I'm sure in pre-calc you've talked about different types of discontinuity: jump, removable, infinite continuity. However, in calculus, when we say a function is continuous, we have to prove three conditions. The first condition that we have to prove, if you're asked to justify or prove that a function is continuous, the first thing you have to prove is that the function exists at that point. The second thing you have to prove is that the limit as x approaches that point exists. And then you have to prove that the limit as x approaches that point is equal to the function at that point. And you will need to make sure that you say all three of these if you're asked to determine if something is continuous. In the function that we see in front of us, we see that the limit, we see that f of, I think that's f, is, let's say, 1. We see that the limit as x approaches f from the left and from the right is 1. And since the limit is equal to the function at that point, this function is continuous. Let's do some examples. Well, before we do some examples, let's talk about properties of continuous function. Basically, if f of x and g of x are continuous functions, then if I multiply either of those by a scalar, it remains continuous. If I add to continuous functions, I get a continuous function. If I multiply two continuous functions, I get a continuous function. And if I divide two continuous functions, I get a function that is continuous, provided that g of x is not equal to 0. I remember we can't divide by 0. So basically, you can add continuous functions together and it will remain continuous. You can multiply them or divide them and it remains continuous. You can multiply by a scalar, a constant, and it remains continuous. Now, what we're going to do is we're going to determine if either of these functions are continuous, and if they are continuous or discontinuous, we're going to give a reason why. And remember, the reasons has to be one of the three that we just stated. We cannot say, well, it is not continuous because it has a hole. That is not a calculus definition, and it has to be a calculus definition. Okay? So the first thing we notice is that in this first problem, x squared minus 9 over x minus 3, your little minds probably are already thinking that this has a hole at x equals 3. Why do we think that? Because if we factor, we get x plus 3, x minus 3 over x minus 3. Okay? So you're probably thinking, well, I know this is discontinuous because it has a hole. But wait a minute. This says that this function is defined everywhere except x equals 3. And when x equals 3, then the function is 8. So just because this function has a hole at x equals 3 does not make it discontinuous. I have to look at the three conditions. So the first thing I have to look at is the limit as x approaches 3 from the left, and I have to look at the limit as x approaches 3 from the right. Well, because this is continuous everywhere except for, if this is defined everywhere except for x equals 3, then the limit as x approaches 3 from the left is going to equal to the limit as x approaches 3 from the right. So basically, I can do a direct substitution. Once I factor this out and they cancel, the limit as x approaches 3 by direct substitution is 6. So this limit is 6. So the limit as x approaches 3 is 6. So the first one part of the condition is met. The limit exists. So the limit does exist. Now the second thing says, does f of 3 exist? And it does, because f of 3 is equal to 8. So the second part of the condition is met. Is the third part of the condition met? Is the limit as x approaches 3 equal to f of 3? And we can see right now that it's not. So yes, this is not continuous, but it's not continuous because the limit as x approaches 3 does not equal to f of 3. And so that's how we would state that. So if you were asked to justify your answer, you would say the function is not continuous at x equals 3 because the limit as x approaches 3 of f of x is not equal to f of 3, and therefore it's not continuous. Okay? Now I know that might seem like a lot to say, but anytime on the AP exam they ask you to justify something, you have to give them a calculus answer. Okay? So let's see if it's continuous at 2. Now the only reason I'm choosing the endpoints is because this is a linear function. And 2x minus 3, if we were to graph that, we know that it's continuous. This is a quadratic function. We know quadratic functions are continuous on their domain. So both of these are continuous functions. The only question is it continuous at the endpoint? So to find that out, I have to take the limit as x approaches 2 from the left, and I need to know if that's equal to the limit as x approaches 2 from the right. So to find when it approaches from the left, I'm looking for numbers less than 2, and that would be defined in this function, in the top function. So the limit as x approaches 2 from the left, by doing a simple direct substitution, I get 2 times 2 minus 3, which is 4 minus 3, I get 1. To find the limit as x approaches 2 from the right, once again, I just do a simple direct substitution, and I get 4. So I get 1 is equal to 4. And we know that that's not true. So this is discontinuous. So this function is not continuous at x equals 2 because the limit fails to exist. Okay? So we can say the function is not continuous at x equals 2 because the limit does not exist at x equals 2, to be specific. Let's try another example. Again, x cubed is a cubic function and it is continuous on its domain. X and 1 minus x are both linear and they're both continuous on their domain. So the only place that it could be discontinuous would be at the endpoints, -1 and 1. So I have to find the limit of f of x as x approaches -1 from the left, and I need to see if that's equal to the limit as x approaches -1 from the right. So I'm just going to do a simple direct substitution. So if I substitute in -1 for x cubed, I get -1. If I substitute -1 in for x, I get -1. Okay, so far we're cooking with grease. So the limit exists. So the limit of f of x as x approaches -1 is equal to -1. Okay? Now the next thing we have to figure out is what is f of -1? We see because this one says less than or equal to, this is where it's defined. So when it's less than or equal to -1, we're doing a direct substitution, we get -1. So we see that f of -1 exists and it's -1. So is it continuous at that point? Yes. And the way we would prove that, we would say f of x is continuous at x equals -1 because the limit as x approaches -1 is equal to -1, and f of negative 1 is equal to negative 1, since the limit as x approaches negative 1 is equal to f of negative 1. The function is continuous at negative 1. Now you're probably saying that's a lot to say, but you have to say it all to get the full credit. We're not done. The next part is it continuous at 1. So that's the next part that we have to check. So we have to find the limit of f of x as it approaches 1 from the left, and we have to see, is that equal to the limit of f of x as we approach x from the right. Once again, doing a direct substitution, I find that that's 1. Doing a direct substitution, I'm now going to have 1 minus 1, which is 0. Are those two equal? No. Now, because it failed the first part, it is not necessary to go to the next part. It has already failed, so we can stop and we can say the function, so f of x is not continuous at x equals 1 because the limit does not exist. So once it fails one part of it, you don't have to test the other part. Okay? All right. So I want you to pause this video and I want you to try problems, the next two problems on your own. The answers I will display in a second. Okay, welcome back. So both of these was kind of a bust because none of them were continuous. When I take the limit as x approaches negative 1, I can automatically see that those two are not equal. The left-hand limit doesn't equal to the right-hand limit, so it does not exist. The same thing when I take the limit approaching 1. This gives me 3, and that gives me negative 1. So the limit does not exist on either one, so it's not continuous at x equals negative 1 or x equals 1. The same thing for this one. I thought this one would be a little bit more promising, but negative 1 cubed, when this is 0, negative 1 cubed is negative 1, and this would be positive 1, and so the limit, since they're not equal, the limit does not exist, and therefore it's not continuous. Okay, now sometimes you will be asked to find what value of a or b or whatever will make the function continuous. When you're asked to find that, you're going to really do the same thing. You're going to take the limit and set the two limits equal to each other and see if you can't find that value. So we're going to start by taking the limit of f of x as x approaches 1 from the left, because once again, 7x minus 2 is linear, which is continuous on its domain. Ax squared is quadratic, which is continuous on its domain. So the only place that they could possibly not be continuous would be on the endpoint. So that's all we have to look at. So we have the limit of f of x as x approaches negative 1, and we want that to equal to the limit as x approaches 1 from the right of f of x. So I'm going to do a direct substitution. Where I see x, I'm going to replace it with 1. So I get, on the left-hand side, I get 7 times 1 minus 2, which is 5. And I want that to equal to, I'm doing a direct substitution. Now remember, I'm substituting for x. X is my variable. A is not my variable per se. So this gives me a times 1 squared, which is simply a. So in order for this to be continuous, a would have to equal to 5. Okay? So let's write that. If this is 5x squared, we see that the limit, doing a direct substitution, I get 5 here, I get 5 here, so the limit exists. Then f of 1, which would be defined here, f of 1 is 5. Okay? So now I have the limit is equal to f of 1, and therefore it's continuous. The limit is defined, f of 1 is defined, and they're equal to each other, so therefore it's continuous. Let's do another one. Here we have ax squared equals x is less than, when x is less than or equal to 2, and 2x plus a when x is greater than 2. We're going to do the same thing. We're going to take the limit as x approaches 2 from the left, and we want that to equal to the limit as x approaches 2 from the right. Doing a direct substitution, this gives me 4a, because I substituted in 2 for x. And that's going to equal to, substituting in 2 for x again, I get 4 plus a. And now I have to solve for a. So solving for a, I'm going to subtract a from both sides, and I get 3a is equal to 4. So a is equal to 4/3. So what I'm saying is when a is equal to 4/3, this will be continuous. Can I prove that? Well, of course I can. So this would be the limit as x approaches 2 from the left. A is 4/3, so it would be 4/3 2 squared. And we want that to equal to the limit as it approaches from the right, which would be 4/3. Oh, I don't know why I wrote that first. 4/3 plus 4. Are those two equivalent? Well, I hope so. That's going to give me 4 times 4 is 16/3. And 4/3 plus 4, that'll give me 12/3, so that's equal to 16/3. So the limit exists. So then what would be f of 2? F of 2, once again, is defined by the top one, so we've already calculated that. That would be 4/3 times 2 squared, which is 16/3. So we see that the limit exists, that f of 2 exists, and f of 2 is equal to the limit. Alrighty, let's do the next one. I think this one might be a little bit interesting, and we have to call in some of your algebra skills. So once again, we want to start by finding the limit as x approaches 1, because this is linear, linear, and linear. They're all continuous on their domain. The only place where they could be discontinuous is the endpoint. So we're going to take the limit as x approaches 1 from the left, and we want that to equal to the limit as x approaches 1 from the right. So substituting in, I get 1 plus 1, which is 2, and I want that to equal to a plus b. Okay, so I cannot solve for a or b here because I have 2 unknowns and 1 equation. Well, let's see if we can't get another equation. So to get the other equation, I'm going to take the limit as x approaches 2 from the left, and I'm going to set that equal to the limit as x approaches 2 from the right. So the limit as x approaches 2 from the left, just doing a direct substitution, will give me 2a plus b. And the limit as it approaches from the left would give me 6. 3 times 2 is 6. So I have 2 equations, 2 unknowns. When that happens, what do? Well, I go back to my handy-dandy Algebra 1 skills or Math 1 skills. And I solve me a system. I'm going to multiply the top by negative. So that's going to give me negative 2 is equal to negative a minus b. Adding those using elimination, adding this equation to this equation. I'm sorry, I didn't mean to put that negative there. I was trying to put a check there. That's not negative. I'm going to get rid of it. All right, so adding those 2 equations together, I get 4 is equal to a because the b is zeroed out. So if I know 4 is a, going back to my original equation, then 2 is equal to 4 plus b. So b is equal to negative 2. So a is 4, b is negative 2. Okay? All righty. I think I'm going to do one more with you, and this is another systems of equation. Yes, I'm doing one more with you, and then I'm going to let you do the last two on your own. So once again, and if you want to pause this, I would suggest that you pause it and try it on your own. I can tell you if you were in my class, this would be a problem on the free response question. So you may want to make sure that you can do this. So if you want to pause this and do it on your own, and then I'll come back and do it with you. But it's the limit as x approaches 1 from the left has to equal to the limit as x approaches 1 from the right. So as it approaches from the left, we get 2 is equal to, we're just substituting in 1, so we get c plus d. And then we're going to do this again, and we're going to do the limit. Let me do it in red. We're going to do the limit as x approaches, and let me write it correctly. Start over again. All right, we're doing the limit as x approaches 2 from the left, and we want that to equal to the limit as x approaches 2 from the right. So just doing a direct substitution for x, I get 4c plus d, and that's equal to, a direct substitution will give me 8. So I have two equations, two unknowns. So I have 4c plus d is equal to 8, and then I have c plus d is equal to 2. I'm going to multiply the bottom equation by negative so that everything becomes a negative. We're using elimination again. And adding those together, I get 3c. My d 0 out is equal to 6. So c is equal to 2. And then I can go to either one of these and plug back in substitute back in c. So then I get 2 is equal to 2 plus d, which requires d to equal to 0. So my order of pairs, c is 2, d is 0. So like I said, take a minute, pause this, do the next two problems, and come back to see the solutions. Okay, here are the solutions. I got a is -1, b is -2, I got a is 4, and b is 3. Okay, one last topic we're going to cover, and that's the intermediate value theorem. Now, the intermediate value theorem is it makes complete sense. It's a common sense type theorem. But on the AP exam, often you're going to be asked to prove something, and you're going to have to refer back to the intermediate value theorem. The intermediate value theorem, the reason it's in this section is because it only works on continuous functions. The function must be continuous in order for it to work. And it is a common sense type theorem. What it basically says that if we have this continuous function, and I have f of a, and I have f of b, then every point, every intermediate point between f of a and f of b has to exist. So for instance, if let's say this is 3 and this is 1, then upon this graph there's got to be a 2, there's got to be a 2.5, there's got to be a 1.8, there's got to be a 1.7. Every number between 1 and 3 has to be represented on this curve. Every y value between 1 and 3 must be represented. That's what the intermediate value theorem states. So why do we need to know this? It's a nifty little theorem to help you prove zeros. Because if I know a function, if I know f of 2 is -5, and I know that f of 5 is equal to 3, then I know if this function is continuous, then I know there has to be some place between 2 and 5 where there's a 0, where it goes through the x-axis. So that is where we use this theorem a lot. So I'm just going to give you one example. We want to prove we have the function, and this should be written as 2x to the third minus 3. We want to prove that it has a 0 between 1 and 2. In order to prove that, I have to say, well, f of 1 is equal to 2 minus 3, which is negative 1, and f of 2 would be 2 times 8 minus 3, which is 16 minus 3, which is 13. So since f of 1 is negative 1 and f of 2 is 13, there's got to be a 0 in here somewhere, because the function had to go when it was at negative 1 and then it went to 13. So somewhere in there it had to go through 0 at leugst once. Now it could have gone through this 0 several times, but it had to go through 0 at least once. And that's the intermediate value theorem. Okay, so this is what I'd like for you to do. I'd like for you to complete the practice problems from the textbook and the 2 free responses. Okie dokie? And that's it for now, and I'll see you in the next video.